Dear friends, welcome in the class of mathematics. Today we have to see statement and proof of the Cauchy's residue theorem. If we see past year's university question papers, the question state and prove Cauchy's residue theorem has been asked frequently. This question is so important. So see the theorem. Cauchy's residue theorem statement. If a function f of z is analytic inside and on closed contour C except at finite number of poles, say n poles, then integration over C of z dz is equal to 2 pi I summation r, where summation r is the sum of residues of f of z at that finite number of poles which lies inside and on closed contour C. Now see the proof of this theorem. Given that the function f of z is analytic inside and on closed contour C except at finite number of poles, say n poles, right? z1, z2, z3, dash 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 zn be the n poles of that function f of z which lies inside and on closed contour C. Means this function f of z is analytic everywhere inside and on closed contour C except at n points z1, z2, z3, dash 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 zn. Inscribe the circles C1, C2, C3, dash 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 Cn whose centers are z1, z2, z3, zn respectively and radius so small say r as shown in the figure. See this figure. This is the closed contour C. Z1, Z2, Z3, dash 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 Zn are the n poles of that function f of z. So inscribe the circle C1 whose center is Z1, radius r which is very small. Circle C2 whose center is Z2, radius r. Circle C3 whose center is Z3, radius r, and continuing this way, nth circle Cn whose center is Zn and radius r. Here we observe that the function f of z is analytic in the region between this closed contour C and this n circle C1, C2, C3, Cn. Here the function f of z is analytic, and therefore by corollary of Cauchy's theorem we have integration over C f z dz is equal to integration over C1 f z dz plus integration over C2 f z dz plus integration over C3 f z dz plus dash 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 plus integration over Cn f z dz. Denote this is as equation number 1. Now here we have to evaluate integration over C1 f z dz. Let I1 is equal to integration over C1 f z dz, where C1 is the circle whose center is z is equal to z1 and radius is r. So equation of circle C1 is mod of z minus z1 is equal to r. By Lorentz theorem we have f of z is equal to summation n varies from 0 to infinity a n z minus z1 bracket raised to n plus summation n equal to 1 to infinity bn z minus z1 raised to minus n. We can write this term as summation n varies from 1 to infinity bn upon z minus z1 raised to n. And therefore we get f of z is equal to summation n varies from 0 to infinity an into the bracket z minus z1 raised to n plus summation n varies from 1 to infinity bn upon z minus z1 raised to n. Put here n is equal to 1, we get b1 upon z minus z1, n equal to 2, so we get b2 upon z minus z1 raised to 2, and continuing this way, so we can write f of z is equal to summation n varies from 0 to infinity an z minus z1 raised to n plus b1 upon z minus z1 plus b2 upon z1 minus z minus z1 bracket square plus b3 upon z minus z1 bracket cube plus dash dash dash. See this first term as phi of z, and so we get f of z is equal to phi of z plus b1 upon z minus z1 plus b2 upon z minus z1 bracket square plus b3 upon z minus z1 bracket cube, continue in this way. In this Lorentz series, here b1, this coefficient b1 represent the residue of f of z at the pole z is equal to z1. We have to evaluate integration over c1 fz dz. And therefore, integration over c1 fz dz is equal to integration over c1 phi z dz plus integration over c1 b1 upon z minus z1 dz plus integration over c1 b2 upon z minus z1 bracket square dz plus dash dash dash. Denote this is equation number 2. Here, phi z is equal to summation n varies from 0 to infinity an into the bracket z minus z1 raised to n. We observe that this function is analytic everywhere, and therefore this function phi z is analytic over c1 also, and therefore by Cauchy theorem integration over c1 phi z dz is equal to 0. Now we have to evaluate integration over c1 b1 upon z minus z1 dz. Here b1 is constant, so you can take outside of that integral, and so we get b1 integration over c1 1 upon z minus z1 dz. Now if we find this integration over c1 1 upon z minus z1 dz, here c1 is the circle, mod of z minus z1 is equal to r, and so we can write here z minus z1 is equal to r e raised to I theta. Therefore, dz is equal to r I e raised to I theta into d theta. And here theta varies from 0 to 2 pi. If we put in this integral, the value of this integral is 2 pi I. And so, integration over c1 b1 upon z minus z1 dz is equal to 2 pi I b1. So, value of this integral is 2 pi I b1. Now, we have to evaluate integration over c1 b2 upon z minus z1 bracket square dz and continue in this way. If you put these values over these integrals, all these integrals are 0. And therefore, putting all these values in equation number 2, we have integration over c1 fz dz is equal to, this value is 0 plus this is 2 pi I b1 plus this is 0, this is 0, and so we get integration over c1 fz dz is equal to 0 plus 2 pi I b1 plus 0, and therefore integration over c1 fz dz is equal to 2 pi I b1. Here we know b1 is the residue of f of z at the pole z is equal to z1. Say this is r1, and so you can write integration over c1 fz dz is equal to 2 pi I r1. Similarly, if you find second integral, that is integration over c2 fz dz, that value is 2 pi I r2. Here r2 is the residue of f of z at the pole z is equal to z2. Integration over c3 fz dz is equal to 2 pi I r3. r3 is the residue of f of z at the third pole z is equal to z3, and continue in this way. Integration over cn fz dz is equal to 2 pi I rn. And therefore, by equation 1, integration over cfz dz is equal to 2 pi I r1 plus 2 pi I r2 plus 2 pi I r3 plus dash 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 2 pi I rn. Take out 2 pi as a common, and so we get integration over cfz dz is equal to 2 pi I into the bracket r1 plus r2 plus r3 plus dash 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 rn. Say this is summation r, and so we get integration over cfz dz is equal to 2 pi I summation r, where summation r is the sum of residues of f of z at that n poles which lies inside and on closed contour C. And that is the proof of Cauchy residue theorem. Now we have to see some examples. See the first example. Evaluate by using Cauchy's residue theorem integration over c z plus 2 upon z square minus 1 dz, where c is the circle, mod z is equal to 2. Solution. Say this is f of z. Let f of z is equal to z plus 2 upon z square minus 1. Here poles of this function f of z are z is equal to plus and minus 1. Means this given function f of z is analytic everywhere except at z is equal to 1 and z is equal to minus 1. We observe that both these poles lie in this circle mod z is equal to 2. And so we have to find the residues at these two poles. So residue of f of z at z is equal to a is given by limit z tends to a z minus a into f of z. Put here a means first pole, that is 1, and so we get residue of f of z at z is equal to 1 is equal to limit z tends to 1 z minus 1 into f of z. Put the value of f of z. So this is equal to limit z tends to 1 z minus 1 into z plus 2 upon z square minus 1. See this residue as R1, and so we get R1 is equal to this limit. Now find out the factors of this denominator z square minus 1, which are z plus 1, z minus 1, and so we get limit z tends to 1 z plus 2 upon z plus 1. Here z minus 1 get cancelled. Now put z is equal to 1 here, and so we get 1 plus 2, that is 3, and here 1 plus 1, that is 2, so 3 by 2. So value of R1, that is the first residue, is equal to 3 by 2. Now we have to find the residue at the second pole, z is equal to minus 1. And therefore residue of f of z at z is equal to minus 1 is equal to limit z tends to minus 1 z minus minus 1 means z plus 1 into f of z. Put the value of f of z, and so this is equal to limit z tends to 1 z plus 1 z plus 2 upon z square minus 1. Say this residue as R2. Here z plus 1 get cancelled, so limit z tends to minus 1 z plus 2 upon z minus 1. Now put z is equal to minus 1 here, so this is equal to minus 1 plus 2, and so we get 1, and in denominator we get minus 1 minus 1, it is minus 2, and so R2 is equal to minus half. There are two poles, z is equal to 1 and z is equal to minus 1, which lies inside that circle. So we find their residues. First residue is 3 by 2 and second residue is minus half. Now use Cauchy residue theorem, and so by Cauchy residue theorem we have integration over c of z dz is equal to 2 pi I summation r, where summation r is the sum of these two residues, and so we get 2 pi I into the bracket r1 plus r2. Now put the values of r1 and r2. So this integration is equal to 2 pi I 3 by 2 minus half. Make this calculation. So integration over c of z dz is equal to 2 pi I. Here 2 is LCM. So 3 minus 1, which is 2. 2 upon 2, that is 1. So finally value of required integration over c z plus 2 upon z square minus 1 dz is equal to 2 pi I. Now see the second example. Using Cauchy's residue theorem, evaluate integration over c sin pi z square plus cos pi z square upon z minus 1 into z minus 2 dz, where c is the circle mod z is equal to 3. Solution. Consider this is f of z. This integrand is f of z. So f of z is equal to sin pi z square plus cos pi z square upon z minus 1 into z minus 2. Now first we have to find the poles of this function. We know poles of the function are given by taking denominator is equal to 0. So here we get two poles, z is equal to 1 and z is equal to 2. Both these poles, z is equal to 1 and z equal to 2, lies in the circle mod z is equal to 3. So we should find the residue at first pole as well as at second pole. So first consider the pole z is equal to 1. So residue of f of z at z is equal to 1 is equal to limit z tends to 1 z minus 1 into f of z. Now put the value of f of z here. So this is equal to limit z tends to 1 z minus 1 into the bracket sin pi z square plus cos pi z square upon z minus 1 into z minus 2. Here z minus 1 get cancelled. So this is equal to limit z tends to 1 sin pi z square plus cos pi z square upon z minus 2. Say this residue as R1, and therefore R1 is equal to, now put z is equal to 1 here. So this will become sin pi into 1 square, which is 1. So this is sin pi plus cos pi. And here in denominator we get 1 minus 2 means minus 1. value of sin pi is 0, value of cos pi is -1, so this is 0 minus 1 upon -1, and so this is equal to -1 upon -1, that is 1. So R1 is equal to 1. Now we have to find the residue at second pole, that is R2. So residue of f of z at z is equal to 2. Second pole is z is equal to 2. So this is equal to limit z tends to 2, z minus 2 into f of z. Put the value of f of z, and so this is equal to limit z tends to 2, z minus 2 into the bracket sin pi z square plus cos pi z square upon z minus 1 into z minus 2. Here z minus 2 get cancelled. Say this is the second residue, that is R2 is equal to limit z tends to 2 sin pi z square plus cos pi z square upon z minus 1. Now put z is equal to 2 here. So this will become sin pi 2 square, which is 4. So sin of 4 pi plus cos of 4 pi upon 2 minus 1, that is 1. Sin of 4 pi is 0, cos of 4 pi is 1. So this is 0 plus 1 upon 1, means again R2 is 1. So we find two residues, R1 is 1 as well as R2 is 1. Now use Cauchy residue theorem, and so we get integration over C of z dz is equal to 2 pi I summation R. Here summation R is the sum of residues of that function f of z at that poles which lies inside the circle mod z is equal to 3. That is, at the pole z is equal to 1 and at the pole z is equal to 2. And so here we get this is equal to 2 pi I R1 plus R2. We find the values of R1 and R2, put these values here. So integration over C of z dz is equal to 2 pi I 1 plus 1. So integration over C of z dz is equal to 2 pi I into 2, that is 4 pi I. So this is your final answer. This is the required integral. And so we get integration over C sin pi z square plus cos pi z square upon z minus 1 into z minus 2 dz is equal to 4 pi I, which is the required integral. In next lecture, we will see more examples. Thank you.